Welcome to the very first lesson of the ArchAdept Barriers 101 training course. In this first part of the course, we're going to be exploring ARM's so-called weakly ordered memory model, and specifically what this means for us as software engineers, and why ARM would even think to do something like this in the first place. So what do I mean by a weakly ordered memory model? Well, consider the following snippet of C code. So here we have two CPUs, P0 and P1, with P0 wanting to send a message to P1. And if you're wondering why we've chosen those particular names, it's just to be in alignment with how these kinds of scenarios are typically presented in the ARM architecture reference manual. Now, P0 sends the message to P1 by first writing the message to the mailbox in shared memory, and it then sets a flag in shared memory to let P1 know that there is a new message available to read. Meanwhile, P1 is spinning in a tight loop waiting for the flag to be set, at which point it reads the new message from the mailbox. And we can see up here that the mailbox and the flag have both been declared as volatile, meaning the compiler is not allowed to optimize away any of these accesses. Seems simple enough, but what if I told you that in the ARM architecture there is actually no requirement for P0's write to the mailbox to be observed before its write to the flag? So for example, if P0 were to write message 42 to the mailbox and then set the flag, it's entirely valid for P1 to see that the flag is set and to perform its own read of the mailbox, and for that read to then return whatever value was held in the mailbox before P0's write. So that could be some garbage data if this mailbox happened to have just been freshly allocated in uninitialized memory, or it could be some stale old message that was written to the mailbox at an earlier point in time. We call this reordering. So we'd say that P0's write to the flag may be reordered before its write to the mailbox, or equivalently that its write to the mailbox may be reordered after its write to the flag. And this is what we mean by weakly ordered. We mean the order in which memory accesses are observed may not match the order in which those accesses appear in our program code. Now, a common reaction to hearing all of this for the very first time is, what? But isn't that just like completely broken? Yes and no. So, as we'll soon see, there are actually some very well-defined rules dictating how and when memory accesses may be reordered with respect to one another. And we'll also see that in the vast majority of cases, everything kind of just works. That is to say, in the vast majority of cases, either two accesses are forbidden from being reordered with respect to one another, or two accesses are permitted to be reordered with respect to one another, and whether or not those two accesses are actually then reordered by the hardware makes no functional difference on the outcome of our program. But of course, in the vast majority of cases is not the same thing as in all cases, as evidenced by the very example you see on screen here. So in a small minority of cases, like our message passing scenario, it is permitted for two accesses to be reordered with respect to one another, and whether or not they are then reordered by the hardware does make a functional difference on the outcome of our program. And it's in scenarios like these that we'll need to employ special barrier instructions in software to manually enforce ordering between otherwise reorderable accesses. Okay, but why? Why would ARM even decide to define a weakly ordered memory model like this? It all sounds a bit crazy, so there must be a good reason, right? And yes, there are some very good reasons why we might want to do something like this. You see, by permitting accesses satisfying certain conditions to be reordered with respect to one another, we grant CPU and interconnect designers the freedom to implement some very clever and very effective memory access optimizations. Let's step through one such example to see what I mean. So I want you to consider the following two ARM-A64 assembly instructions. Now, depending on your prior experience, I appreciate that this may be your first time seeing ARM-A64 assembly, or indeed seeing any form of assembly. And if that's the case, then you may be interested in our upcoming Assembly 101 training course, due to be published around summer this year. So on that training course, you'll learn step by step and with practical hands-on coding exercises how to write, build, and disassemble bare metal ARM-A64 assembly projects, as well as how to run those projects on simulations of real hardware using QEMU, and how to debug those projects live using tools like LLDB. But for now, in short, the LDR instruction on line 1 is a load, which reads the contents of external memory into a register inside the CPU. And the STR instruction on line 2 is a store, which does the opposite, so it writes the contents of a register out to external memory. The square brackets are kind of like dereferencing a pointer in C and C++, so you can think of the load on line 1 as being x0 equals *x1, where x0 and x1 are registers inside the CPU, and it then follows that you can think of this store on line 2 as being *x2 equals x0. Now, I want you to ask yourself, what are the steps required in order for the CPU to actually perform loads and stores like this when they appear in our program code? Well, first we need to calculate the final virtual address, and granted there's not much going on in the examples you see on screen here, as registers x1 and x2 already hold the final virtual address, but these instructions can actually get quite a bit more complicated. For example, we could have something like this, where we are logically shifting left the value currently held in register x5 by 3 bits, and we're then adding that resulting offset onto the base address currently held in register x4. So when we say calculate the final virtual address, we mean reading the values in each of these registers and then performing any necessary arithmetic. Next, we need to translate that virtual address into a physical address, and this involves the memory management unit, the MMU, first looking up the virtual address in its translation look-aside buffers, the TLBs. If we miss in the TLBs, then we'll need to wait for the MMU to walk the page tables in memory in order to generate a fresh end-to-end translation for that virtual address. And once we have the physical address, we'll also need to wait for the MMU to perform its various checks. So checking things like, are we trying to write to read-only memory, or are we trying to access privileged memory from user space, and so on. Assuming all of those checks pass, then we can finally issue the load or store to the external memory system. And in the case of the load, we'll have a fourth step here, which is to write back the loaded value into the specified destination register, ready for later instructions to either consume or manipulate in some way. Now, I want you to imagine a CPU design in which all 4 of these steps must have completed for one memory access before we're able to begin working on the next memory access. And then consider what's going to happen if we were to execute a snippet of C code like this, where we are reading the values of 4 non-overlapping integers from memory. So we'll first need to perform all 4 steps for read A, then perform all 4 steps for read B, and so on. Now, clearly, this is a less than optimal use of available CPU resources. For example, when we're translating a virtual address to a physical address, then the CPU logic for calculating the final virtual address and for issuing a load or store to the external memory system is just sitting there unused. Similarly, when we're issuing the load to the external memory system and we're waiting for a value to be returned, not only is the CPU logic for calculating the final virtual address sitting there unused, but so is the CPU logic for translating a virtual address into a physical address. So we can do better here. And one way we can do better is by breaking this operation down into smaller chunks or stages in the CPU pipeline itself. So in a CPU design like this, we're able to issue read A to the pipeline first, which begins calculating the final virtual address. And then as soon as that's done and read A has progressed onto the next stage of the pipeline, then we're able to immediately issue read B to the first stage of the pipeline. And that means we're translating the virtual address for read A at the same time that we're calculating the final virtual address for read B. And similarly, as soon as we finish translating the virtual address for read A and it's progressed onto the third stage, that frees up the second stage for read B, which in turn frees up the first stage for read C. And this is going to keep going until we've handled all 4 loads. Now clearly, this design makes much better use of available CPU resources than before, but it's still less than ideal. So what do you think the problem here might be? Well, I want you to consider what would happen if read A here were to, say, miss in the TLB, forcing the MMU to walk the page tables in memory to generate a fresh end-to-end translation for that virtual address. That takes time, and read A cannot progress onto the third stage of the pipeline until that process is completed. And in turn, read B cannot progress onto the second stage of the pipeline until read A has vacated it. So it's not just read A that's blocked here, read B is blocked too. And this is despite the fact that we may actually already have a translation for read B waiting for us in the TLB. So if only we could get read B to progress onto the second stage of the pipeline, we'd hit on that entry in the TLB and we'd be able to immediately proceed with issuing read B to the external memory system. Furthermore, read B being blocked here also means that reads C and D are blocked too, because we're unable to issue them to that first stage of the pipeline. Again, despite the fact that we may actually already have end-to-end translations for those reads waiting for us in the TLB. So in effect, all three of reads B, C, and D are being unnecessarily blocked by read A missing in the TLB, possibly for hundreds or even thousands of clock cycles, depending on things like how many levels of page table we're using and whether or not the MMU page table walker hits in the data caches while walking those page tables in memory and so on. So what can we do about this? Well, one thing we could do is simply copy-paste the load store pipeline so that we can process multiple memory accesses in parallel, right? So this is analogous to having two lanes on a road or highway and being able to use one lane to drive around an obstruction in the other lane. So now what we can do is issue both reads A and B at the same time, read A to the top pipe and read B to the bottom pipe, and these two pipes then progress independently. So once read A progresses onto the second stage of the top pipe, we can issue read C to the first stage of that top pipe. And similarly, once read B progresses onto the second stage of the bottom pipe, then we can issue read D to the first stage of that bottom pipe. Crucially, this means that when read A gets blocked on the second stage of the top pipe, reads B and D are actually able to continue progressing through the bottom pipe. And depending on how clever our pipeline logic is, we may even be able to detect the fact that read C is blocked by read A on the top pipe and reissue read C down on the bottom pipe. And these three reads can then progress through the bottom pipe until they've all been handled. And of course, sometime later, we'll eventually finish translating the virtual address for read A will become unblocked, and it'll be handled too. But hang on a minute. In our code, we first read A, then read B, then read C, then read D, but we just saw that as these reads progressed through our dual issue load store pipeline, the actual order in which they were issued to the external memory system was B, D, C, A. So in effect, the CPU has reordered read D before read C, and all three of reads B, C, and D before read A. And this is one of the reasons why the ARM architecture defines a so-called weakly ordered memory model, in which memory accesses satisfying certain conditions are permitted to be freely reordered with respect to one another. Because in doing so, we grant CPU designers the freedom to implement memory access optimizations like this. If loads had to be observed in program order, then CPU designers would not be able to implement a dual issue load store pipeline like this. Or they'd have to do something like somehow detect the fact that read A had gotten blocked in the top pipe and correspondingly block the bottom pipe to prevent reads B and D from progressing too, but that all starts to get really complicated when the whole point of this was that we wanted these two pipelines to be able to progress independently of one another. Now, something I want to emphasize here is that this dual issue load store pipeline is just one of many different memory access optimizations that are enabled by permitting accesses to be reordered. So for example, we may have a CPU design with only a single load store pipe, and it may be that we're executing a code sequence with 4 writes to non-overlapping integers in memory rather than 4 reads. Clearly, in this example here, The CPU is going to issue write A to the external memory system first, then issue write B, then write C, and finally write D. And yet, the actual order in which some external agent observes those writes may not be the same order in which the CPU issues them to the external memory system. Meaning, some external agent may, for example, observe write B before observing write A. Now, I can hear you asking, Ash, how can that possibly be? Well, you see, permitting accesses to be reordered does not just grant CPU designers the freedom to implement some very effective memory access optimizations. It also grants interconnect designers the freedom to implement some very clever and very effective memory access optimizations as well. And indeed, it's therefore possible for the interconnect to reorder our memory accesses at a system level, even if we don't reorder them within the CPU. So join me in the next lesson where we'll step through some examples of that in action. I'll see you there. Thank you.